Picture yourself riding in the passenger seat of a car. If you glance over at the driver next to you, they look perfectly stationary. But turn your head to look out the window, and the trees, houses, and streetlights are tearing past you in a blur. It's a strange contradiction. Compared to the driver, you aren't moving an inch. Compared to the world outside, you are flying forward. In physics, we resolve this using a reference point. This is simply the baseline object or environment we use to judge whether a state of rest or a state of motion is occurring. Because movement depends entirely on which reference point you choose, true stillness doesn't exist. To understand how things actually move, we have to build a scientific framework to map their paths. We start with translatory motion. This happens when an entire body shifts completely from its original starting point to a new location. When that displacement happens exclusively along a perfectly straight line, it's classified as rectilinear motion. Think of a high-speed train accelerating down a completely straight track. Every single car is covering the exact same linear path, but trajectories aren't always straight. When translatory movement follows a curved trajectory, it becomes curvilinear motion. The moment our train banks around a bend, its overall coordinate is still changing permanently, but the path it takes is now an arc. Tracking these translatory paths gives us the baseline geometry required to map any object that permanently changes its location. Not all movement results in a permanent location change. Circular motion follows a continuous looping path that constantly comes back on itself. If the fixed axis of rotation is located inside the moving body, it's called rotatory motion. The blades of a windmill spin rapidly, but the mechanical center point they rotate around is housed inside the structure itself. Alternatively, if the axis sits outside the moving object, it becomes revolutionary motion. A child riding a merry-go-round is revolving around the machine's central pillar rather than their own internal center. Sometimes a path is repetitive but doesn't make a full circle. Oscillatory motion is a back-and-forth fluctuation across a center resting spot, known as the mean position. A swinging pendulum continually crosses that mean position over and over without ever moving permanently out of its location. And then there are paths with no predictable pattern at all. We define this as random motion, the erratic flight of a housefly, pollen grains drifting in water, or a dog chasing a cat. By categorizing these movements, whether they are internal loops, external orbits, fixed swings, or total chaos, we can predict the physical behaviors of things that rarely travel in straight lines. Knowing the shape of a path is only half the equation. We also have to measure the rate at which an object travels across it. This chart shows uniform speed. The vehicle covers identical, equal distances over identical intervals of time. Exactly 40 kilometers is crossed every single hour, without deviation. In reality, friction, traffic, and obstacles force objects to speed up and slow down. This creates non-uniform speed, where unequal distances are covered in those same time intervals. To make sense of that chaotic stop-and-start reality, we use this formula for average speed. We divide the total distance covered by the total time taken. We can apply this to rapid biological bursts. A cheetah sprinting 120 meters in 4 seconds has an average speed of 30 meters per second. It works over long mechanical hauls, too. If a train travels 330 kilometers between stations over 5 hours, its average speed is 66 kilometers per hour, accounting for all the stops and slowdowns along the way. Calculating average speed smooths out the variations of physical movement, providing us with a single functional metric to understand pacing. In the physical world, objects rarely stick to just one of these motion categories in isolation. Look at a rolling bicycle wheel. It exhibits rotatory motion as it spins around its central axle, while simultaneously executing translatory motion as the entire wheel moves forward down the street. To see the most extreme example of this simultaneous multiple motion, we just have to zoom out. Our own planet is constantly spinning on its internal axis, giving us rotatory motion. But it is also traveling through space in a massive orbit. That massive orbit is anchored by an external reference point, the Sun. So Earth is also executing continuous revolutionary motion. Because the ground beneath your feet is perpetually rotating, revolving, and translating through space, absolute stillness is entirely impossible. So with all these overlapping motions happening right now, are you ever truly standing still? Let us know what you think in the comments below, and hit like and subscribe for more.